Okay, we'll add a few numbers here, and if you're very young and listening to this, the numbers may get a bit overwhelming, so you can just skip it or listen to it and understand as much as you can. So before we do the energy budget for the earth, which we already discussed in different ways, let's look a little bit at clouds. But what is budget? I should explain that. I think you understand. Budget is where you look at what is coming in and what is going out and look at how they are balanced. We talked about the parents' income first. Let's say parents are getting some income. They pay for the house, for the rent, for the car, for the food, for your education, and they may give you some pocket money or spending allowance and so on. And then they have to worry about the future, so they want to save a little bit of money and so on. So that's the budget. The countries have to worry about budget at a very big scale and so on. So energy budget, as we mentioned before, is basically looking very carefully at the energy that is coming in from the sun, shortwave, and the energy that is going out from the earth as long wave, and see how much we are keeping, how much we are sending back. Okay, if we keep more and more, if your parents keep more and more of the money, the savings grow. But if we keep more and more of the energy from the sun, then the temperatures grow. And that's not always a good thing, right? So we will talk about it more. But coming back to how the water vapor, evaporation, and circulation, convection in the atmosphere work, you have different kinds of clouds. Every day you go out, unless you are living in a real desert or a place which has very little rain, you are always going to see some clouds. Some look very high and very thin, some look very deep and dark, and some look very fluffy and white. And now in monsoon in India you will begin to get darker and heavier and scary looking clouds. How do they form? We already mentioned it a little bit. As we said, sun's energy, 48%, is reaching the surface, causing evaporation where there is water. And evaporation, remember we said, is energy that is being taken out of the water and the surface. As the air rises, you can imagine that the surface has higher pressure than if you go up. How do you know this? If you take a balloon, let's say it's filled with a lighter gas like helium, you may have done this in your birthday, even though now you get a lot of warnings saying don't release the balloons because they end up falling in the water and causing problems for fish or other animals and so on. But nonetheless, for our experiment's sake, if you fill a balloon with a lighter gas and release it, it will start to rise, because it has something called buoyancy. Like the water we saw before here, warmer water is lighter, which means it's got buoyancy, so it will try to rise. And colder water is heavier, so it will try to sink. So it has buoyancy that will make it sink. This has buoyancy that will make it rise. So when the surface gets heated, the air gets warmer and it rises, and it has some water vapor. Pressure decreases as it goes up away from the surface. Pressure decreases means what? Just like the balloon will begin to expand if the pressure is lower. Imagine that you're holding the balloon like this and you let it go and fill more air, it begins to expand. So when the air expands, does it cool or does it warm? Think about it. You may be too young to think about it, but some of the older kids should be able to think about it. If the air is rising and it expands because it's in a lower pressure, then the temperature drops, it gets cooler. And if it has water vapor, does the water vapor condense? It should, right? There are many scientific details about humidity, saturation, and so on. Somebody is playing the TV, so let me go and ask them to turn down the volume. I have guests. Ah. Sorry about that. Let me make sure I'm in the frame. When I record, I have to try to be in the frame. So let's go back. So when the air rises, warm hot air with humidity rises, the water vapor condenses, which is why it forms clouds. Depending on whether the air is coming down like this or it's just going up, the cloud can reach several levels in the atmosphere. Here we are looking at 10,000 feet or 3 kilometers, 6.1 kilometers, 9.1 kilometer, 12.2 kilometer, and so on, just arbitrarily chosen. So you begin to build a cloud. It can have a positive feedback inside. Let me just explain it. If you don't understand it, don't worry about it. So as the air, warm air with water vapor rises, water vapor condenses. What happens to that? The latent heat, the heat that is there with the evaporation, is going to be released, which means energy addition makes the air even warmer, so the air can rise even further. So you can have this rising air keep on going. So that's what we call mature stage, and at some point it cannot rise anymore. You can think of the room, for example, has a ceiling. If you are boiling water in an open pot, water vapor is rising, air gets lighter near the surface of the hot water, air rises, it hits the ceiling, then it has to go sideways and come back. So that's what happens. The atmosphere has kind of a ceiling. Some of you may know what that is called, but let's not get into that there. So that ceiling, and then it sinks on both sides, and then you can have a dissipating stage. So this is just to tell you that there is a circulation happening because of the convection in the atmosphere. So those also move the energy around. It's not just solar energy coming in, thermal energy going out. Energy is doing some work and creating these circulations, and later on we'll look at winds and see that winds can also move energy from the ocean onto land, from the land onto the ocean, and so on and so forth. So here we are thinking slightly differently, and again, these are numbers. If you are very young and haven't learned to deal with these kind of numbers, don't worry about it, just think about it. Let's say the amount of energy from the sun is, we said it's 340 watts per meter squared per unit area. It could be square feet, square inch, square kilometer, whatever, but per square meter it's 340 watts. Let's say that's 100%. So your salary is 100%. We said about half of it gets to land, warms everything and so on, and tries to send it back. 64% of that is eventually going out, with 6% escaping directly. But we also said that some of it is reflected in the atmosphere itself because of bright clouds and so on. Sorry, that's different. There are particles and molecules that are reflecting. There are certain molecules like sulfates which are reflective, so they scatter the sunlight. There are clouds which are reflecting 20%, and reflected from the Earth's surface is about 4%, so that is 30%. That is the average albedo of the Earth, right? And the energy absorbed by the atmosphere, like the greenhouse gas molecules, they are going to get warmer and emit energy. The energy absorbed by the cloud is going to produce some thermal energy, and there is some conduction and rising air. Rising air is the convection. Let's forget about conduction because it's never very important. I think you understand. Maybe it's important to explain what is conduction and convection. You may have heard of it, electric conduction and so on. If you take an iron rod, don't do this on your own unless you are grown up enough, and if you start warming it at one end, eventually the heat will start moving, temperatures will keep increasing along the iron rod to the other end. What is happening? Conduction is happening. So molecules here get warmer, they begin to vibrate because they get warmer, and they are not really leaving the iron rod, they are just vibrating and transferring the energy to the next molecule, to the next molecule. So you are conducting the energy towards the colder end, whereas in convection, water molecule is actually lifting and taking that energy somewhere. Right, so you have conduction and rising air. Rising air is basically convecting. It is taking the energy from the surface and rising and releasing it. Okay, so carried to the clouds and atmosphere by latent heat in the water vapor is 23%, and so on and so forth. Should you remember all these numbers? Well, it's good if you can, but you should remember the physics and the concepts. Energy coming in from the sun is 100%. Energy going out has to be also the same. So you can see here reflected sunlight plus outgoing thermal energy should add to 100% because it's in balance. If it is not in balance, that means energy coming in is not all going out, which means we are trapping some of the energy like the blanket, and it's making things warmer, which is why you use the blanket. But on Earth, when you trap energy and make it warmer, you mostly have bad consequences. Also, some places will have good consequences, which we will not get into here. Okay, so you can put numbers on these as well, which I'm not going to do, but I will just point out that the energy coming in is 340 watts per meter squared at the top of the atmosphere before it enters the atmosphere. But here in the thermal energy that we are computing, you can see that there is a number of 398 watts per meter squared emitted from the surface. How did you take 340 watts per meter squared energy coming in and create much more energy as thermal energy? Right? That's the magic, and that's exactly what the blanket does. If you are not putting on a blanket, the atmosphere, the air in the room is making you feel cold because your body is losing the heat directly to air. But when you put on the blanket, there is no extra energy. It's still the energy of your body, but instead of letting it directly exchange with the air in the room, you are going to trap it within the blanket so you can amplify the thermal energy. You see, it increased. Similarly, energy coming in from the sun is being trapped by the the Goldilocks blanket or the greenhouse blanket. It's bouncing around or is being trapped, and the number can be larger than what it came in. What matters is when it goes out of the atmosphere, it has to be the same as what came in. That's the budget. Otherwise, it will get very, very warm, and with greenhouse gas increases, that's what we are doing. We are sending less and less energy out, keeping more and more of the energy coming in, and hence we are causing global warming. I'm saying this in many ways because it's important. And quickly look at the reflected radiation. Where there is high albedo, you have higher reflected energy in watts per meter squared. This is energy now over the region, so it's not the same as the flux at the top. Okay, so it's averaged over a larger area. Okay, so 700 watts per meter squared, and you can think of it as global averaged over the surface of the earth. No, actually that's watts per meter squared, so it will be averaged over time, over a year or so. Annual mean we call it. Emitted radiation, here you can see that there are regions where there are tall clouds which emit less radiation. There are deserts and other parts where there is more radiation, thermal radiation. How do you explain this? Remember, thermal radiation is related to temperature to the power of 4. If you increase the temperature by 2 degrees, it will increase by 2 to the 4th, right? 2 squared 4, 2 to the cube 8, 16. So 2 degree increase will increase the energy by 16 times. That's how you have to remember it. Okay, so we'll come back and see a few more details of how this energy actually gets distributed. We are always talking about averaged for the earth because it's easier to track the budget. Let's say your mother is earning some money, your father is earning some money, and maybe your brother is earning some money, and doing the budget from the family will be easier if we average all the income and all the outcome or all the expenditure rather than taking each income, each expense separately. So when we do all of the earth, it's easier to compute the whole budget. But not everybody in the family is spending the same amount. Your brother is going to work, taking a scooter or a car. Mother is going somewhere and doing something, father, and you are going to school. So everybody is not spending the same amount of money. So the budget of the energy is also not causing the same amount of warming everywhere. So we'll come back and see that. Okay, again, listen carefully, make sure you understand the concepts, and ask questions if you don't understand. Okay, see you in the next podcast.